Good afternoon, everybody. I hope you have had a good time so far. Let's talk a little bit about hardware. I'm going to talk about what Gapwaves has done during the last years on the new generation of imaging radars using waveguide technology. First, I give you an introduction about Gapwaves and the way that we see the trends on the imaging radars. There will be, of course, some challenges and, of course, some opportunities for us as a hardware company. We have a new sensor, worked with Sens Strat, Sens Strat Hyogin D1. I'm going to talk about its performance and give you some concluding remarks at the end. Gapwaves was founded by Professor Persimmon Kildall at Chalmers University, Gothenburg. And it was listed in the stocks market in 2016 when everything was more serious afterwards. And we have had more and more patents every year. And we specialize in the millimeter wave antenna solutions for telecommunication and especially in the automotive radar industry. In the automotive radar industry, we have some customers, tier 1 customers. The names that I can tell are Under, Forvia Hella, Bosch Veoneer, and Smart Micro. We think that whoever that uses our antennas can sense better and can fit the whole module better, and we will have a better build-up scenario. So you can see further, you can see broader, you can have a better beam control to detect objects. Gap waveguide gives you a wider bandwidth performance and better resolution. When it comes to waveguides, which gives you the minimum possible actual loss in your system, there are 3 ways of doing it. Because there is a routing system, you need to make it in layers. And to make it in layers, you should cut the waveguide at some point. The best way is to cut it at the middle of the longest dimension of the waveguide to have the minimum leakage possible. In the high frequency of 80 gigahertz, the leakage can cause many signal fluctuations for the radar. But the problem that the gap waveguide technology fixes is that if you remove 2 of the walls on the left and right and replace it with a periodic structure, you basically have the performance of a solid wall. And that allows to have some gaps between the layers as well without any leakage. So assembly-wise, it helps. But after that, the next step for us was going to let go the waveguide per se, but start to work with the coaxial lines, which gives you a TEM mode performance and a wider bandwidth, which we call it multi-layer waveguide technology. You see in the picture from the left the conventional hollow waveguide thickness, the EuMW or injection molded waveguide that Gapwaves has developed in the past, its thickness, and on the right side you see 3 metal sheets over each other that can realize the coaxial performance here. It is very cost effective, this method, and it's very fast for the manufacturer. I'm going to talk more about it. And imaging radar, thanks to all other presenters, maybe I can skip this part, that it's all about the imaging radars as you saw today. And there's a push to reach to a better imaging radar performance. And for the imaging radars, the challenges so far are how can we detect a stationary object in the middle of a dense clutter, like a dropped cargo? How can we resolve objects in height, like bridges that we saw today? How can we track better and classify better, which means better resolution? And how can we improve the detection range to increase the TTC, time to collision, so the driver can have more time to react if there is some accident? And for that, you need more and more range. And we need a wider bandwidth to do all these things. when it comes to the size, we are talking about in the order of 50 lambda, 48 lambda. That gives you 1.2 degree of resolution in whichever the direction that you increase the size of the radar. If you use microstrip lines, CPW lines, it will be lossy. There will be dielectric loss, and you will use expensive RF substrates. But using Waveguide, you can remove that part and improve the performance by reducing the loss and increase the range. There shouldn't be a lot of leakage between the TX and RXs. And our technology allows to reduce the coupling between the active channels. And another thing, as an extra, is that the structure will be partly metallic or fully metallic, so it helps for the thermal handling. It's partly metallic or fully metallic, so it helps for the EMC as well, something that the substrate antennas, substrate-based antennas cannot provide. So it's ideal to use waveguide structures, and I suggest to use Gapwaves technology. But whatever that is, you need to use the waveguide antenna to solve all these problems for the imaging radars. Yeah, there is a trend, interesting trend that comes from ID Tech X. If you check the bars that are increasing, here, no, here. So this line, this part is increasing, which means that the radars that they use a lot of virtual channels, more than, I don't see the number here, maybe 192, it will increase yearly. So in future, there will be some imaging radars that have hundreds or thousands virtual channels to achieve all these challenges that I talked about. Performance-wise, of course, the waveguide antenna has a good electrical performance. It reduces the losses. The coaxial line can give you even wider bandwidth. And in terms of loss, it's 10 times less lossier than the printed structures. And the full band of 76 to 81 is easily achievable with this structure. You have flexibility to design and engineer the radiation patterns in both planes, azimuth elevation, to reduce the bandwidth or increase it or shape the pattern in any way. And when it comes to the spacing, of course, to have the minimum angle ambiguity, you need to have a better, closer elements next to each other, half wavelength, which is completely possible with the Gapwaves technology, EuMW or mmWave. And as I said, it can provide some other features like cooling and EMC shielding. And of course, if you need to improve the similarity of the patterns, you can embed some termination in the structure to keep the similarity of the radiation patterns. Metal-based coaxial waveguide antennas offer exceptional electrical and thermal performances. Here on the back, you see a radar made by Arbe. It has, I guess, 96 channels, 48 TX, 48 RX. You see the patches on the left side, left bottom side, you see the top side, and on the right upper side, you see the back side of the same antenna. You see the density of the antennas and the problems that these dense routing can cause in performance. Another thing is that when we are talking about the imaging radar, we are talking about a massive structure. Here on the back, you see a structure on the copper part, the yellowish, or whatever the copper is. That color is for corner radar with 4 TXs and 4 RXs. But but on the back, the aluminum part is 2 by 5 chipsets next to each other. You can see the massiveness of this structure. Yeah, so we are going from 16 virtual channels, 4 by 4 TXRX, to up to 2,300 virtual channels, 48 by 48. It will be very complex, of course. It's a headache for any designer that designs this in the printed microstrip structure or in the waveguide. There will be about the RFICs. Sometimes there is one RFIC with many TX and RXs, like the one that Under uses, 16 by 12 RxTX, or the one that Arbe has used in the previous picture that has 24 TX and 12 RX. Or sometimes you can combine the NXP or TI chipsets. Each of them has 4 channels. So you saw different scenarios so far in the morning. But for all of them, the antenna needs to be somehow attached to the RFIC using a transition. And then inside of the antenna, you need a complicated routing, layers over layers. So it's very important that you should have a scalable design and idea, which we believe mmWave provides in this case, and you can have improve the robustness. TEM mode coaxial line helps in that sense. And last year or the year before, we presented the automated testing that we have at Gapwaves, that how fast we can measure such a big structure with many ports in less than a minute. And another strength of this idea, which that uses many copper layers over each other, is its thickness. On the left is a typical molded antenna in waveguide, which obviously is another design. But if you consider just one of the layers on the left side and compare it with the whole thickness of the antenna on the right side, you see how thin the whole idea will be. On the right side, you see 4 layers of copper over each other. You see the welding spots that we use to keep all the layers together. Did I miss anything? So the area has increased. Per side right now, before we were like 5 by 5 centimeters, but right now with the radar, one of the dimensions can be 20 centimeters, or both of them at the same time to improve the resolution. The density has increased in the imaging radar as well. Before in the 5 by 5 we had 8 physical channels. Right now we have 96 channels, 100 channels. So the density of the elements has increased by the factor of 2. Just imagine how hard could it be just to connect all these points to each other in such a high frequency. And this solution is flexible, meaning that we heard that there are some companies that they like to have just one big MMIC with many ports. There are some companies that they like to have different radars with some resolution in the elevation, so one here, or azimuth, one here. Some companies that like to use this distributed aperture radar thingy that we heard today. And so it's just, we need a solution that can react to all these scenarios, which mmWave technology is doing it. So in that sense, it's a more flexible one. It doesn't matter what are the positions of the antennas, like if they are distributed regularly or sparse array. It's just a matter of if you have enough room to do the routing, you can do it. With the integration toward MMIC, we see launcher packages and launcher packages coming from NXP, from TI, other manufacturers. We have worked with them, and this structure can be used for them. Some cases, in the older versions of the MMICs, you need a transition. At Gapwaves, we have the transitions from the microstrip to the waveguide as well. And one other thing is that when it comes to such a large structure, you need a good reaction time for the customer. Like, they come to you, and if you use a molding, you should say, okay, wait for some time, so I design and then make the tooling and then I start to produce. But this one, it's much faster, because the difference between the first prototype that we make and the last one that we make in the mass production is not that much in terms of just making the layers. What happens in the mass production is just the assembly method that is getting more complicated, not the design. So in that sense, it's a very flexible solution as well. So the upfront and running costs are much lower compared to the molded antenna. On the back, you see the demonstrator from NXP with 4 TX and 4 RXs. The TXs are separated in a line, but the RXs are more distributed. Different designs, as you see, the antennas are different. Then come to the Sens Strat, which is a daughter company of Gapwaves, which with so much focus on the sensor. You see the structure on the back, the PCB part. They are using RBA chipsets, 24 ports per TX chip and 12 for RXs. So 4 RX chips and 2 TX chips. 96 RXs, 96 TXs. The TXs are on the left side in the columns in a row over each other, and the RXs are at the bottom and the top. It's a regular distribution, so it allows you to not have grating low. A very wide field of view without any grating low. It has 4 different modes, but in terms of the antenna, it can provide 1.2 degree in the resolution of the azimuth and 1.5 degree in the elevation. Something that you couldn't achieve before with the corner radars because the size is smaller. In terms of range, it can go up to 340, but of course there are different modes to detect different objects and classify them. And the field of view in the azimuth is 100 degrees, minus 50 to plus 50, and in the azimuth, in the elevation is 30 degrees. So it is massive. It is a huge antenna. The dimension is 13 by 11, but over there it looks big, but it's just this size. In terms of wavelength, it's huge, but yeah. I mentioned, I guess, everything here. We use the coaxial mmWave, as I said. There are 2 layers of the routing to reach each antenna from the MMIC on the back. 1 layer for TX, 1 layer for RX, so we can isolate them from each other very good. And there is 1 bottom layer that provides the transition to the PCB side, and 2 of the top layers are used to realize the antenna radiators, TX and RXs. The interface is PCB launchers, so they are not launcher in package. And I'm gonna show you some of the performance results, but it's just from the pre-production units that we recently had. You see all the 6 layers of the antenna over there. 1, 2, 3, 4, 5, 6. Yes, and from bottom to top, you see the pins that are existing here. So on the back of this layer, there are some other pins, and this is the coaxial line, something that I presented before. The first layer of routing, the second layer of routing would be the 4th one, and the top 2 are the antenna layers. You see the radiation pattern, the average radiation pattern for all the channels of the RX on the top, and for the TX, the bottom, for different frequencies. You see the stability of and similarity of the stability of the radiation patterns over the frequency, both in the elevation and in the azimuth. Because of the different size of the RX and TXs, there is a different beam width in the elevation, as you see. To validate the performance, as I said, we have checked some samples of this antenna. On the picture, on the back, you see the density of this piping routine that we have. You know, it's like plumbing to realize this routing. But thanks to the stability of the idea of the mmWave using coaxial line, it's very easy to go from 1 layer to another one, do crossover, go down, go up again, because most of the components in this design are very, very stable with frequency. You see the S11 on the top. for different different units that we have from the pre-production, and this is what we call STU1, but it basically means that we put all the antenna channels and we just check the broadside gain to check the similarity of the samples. It somehow shows the gain. But what matters here that should be seen is that the similarity of the gain of the antennas are in the order of plus minus 0.5 dB in the broadside. I'm going to show you some sensor performance. So with a single walking pedestrian in the range, when the range is designed to the waveform is chosen to be covering from up to 120 meters in the range, and the pedestrian that is walking 45 degrees from the radar, so at the edge of the field of view, with the range resolution of 30 centimeters, so more or less, yeah, I don't know what is this dimension of the body, but that. And then there is this beamforming mode that we use for this one, which we combine 3 of the TXs each time to have a higher gain for the TX part. Yeah, you can see this is my colleague walking on the left. It's in the street, so you see some things that are walking by as well. Yeah, we are all dots to the radar. And then next one. Sometimes it happens that a pallet, is pulled away from the truck ahead of you. So this is the case that one of my colleagues is just pulling a pallet on the ground from the long side, lying on the ground, I mean, with the same setup, more or less. So, and it can follow the pallet up to 118 meters. Here in this case. As I said, it's a pre-production unit. There are a lot of things that are happening. Please follow us. There will be a lot of development about this one, especially on the signal processing part, with much more complicated maneuvers for the performance of the sensor. The playback was 5 times more than the reality, so my colleague cannot pull the pallet that fast. Conclusions. But before that, I can show you the antenna over the PCB. You see the antenna on this part, and there is a spacer here, which keeps the antenna over the components on the top side of the PCB, and of course the connector and stuff on the back. But you see the thickness of the antenna over the radar sensor, 6 layers, and doing a lot of crossovers for about 100 channels. I'm going to conclude. And so you see the imaging radar trend today. Of course, every challenge that you have talked about today, we see it at Gapwaves as an opportunity that we can, the more complicated the imaging radar, the more complicated the routing, so mmWave can show its potential better. There are a lot of players in the market, and these challenges are not only the electrical performance, but other things should be added. This metallic structure on the sensor, there are some thermal pads at the bottom, so it helps for the thermal handling of the MMICs that are, I mean, here we saw just one performance, but this sensor should work for hours. It gets hot, and this metallic structure helps a lot to cool down the mmWave. We think that it's the largest in terms of the number of channels, the Huygens D1, and in future you will hear about it more on our websites or on the papers or presentations.